Hi, 44con. So this is See No Evil, Hear No Evil, hacking invisibly and silently with light and sound. So my name is Matt Wixey. I lead vulnerability research for the cybersecurity practice in PwC UK. I also run a research blog called the Dark Art Lab, which looks at the more exotic and esoteric aspects of security research. I've been at PwC for about a year. I also work on their pen test team. Prior to that, I worked in law enforcement in the UK, leading a technical R&D team. So what I'm going to cover today is 4 sections. Part 1 is going to be looking at different ways to jump air gaps using light and sound. Part 2, surveillance and counter surveillance, looking at laser microphones and infrared motion detectors. Part 3 is BANTs. So that's stuff that I've come across over the course of this research that's amused me. Admittedly, that's quite a low bar, as you'll see throughout this talk, but hopefully you guys will enjoy that too. And then I'm just going to sum up and give some ideas for future research as well. So a couple of disclaimers. The views and opinions in this talk aren't necessarily those of PwC. All the content's for educational purposes only. Be sure to check legislation, etc. This presentation isn't to do with 0 days or even vulnerabilities necessarily. It's more about manipulating the inputs and outputs of systems that use light and sound in order to have a desired effect. And lastly, I am in absolutely no way an electronics expert. I see magic smoke so much that it's not even magical to me anymore. Regularly kind of poke myself in the eye with resistors and burn myself with soldering irons and that kind of thing. So to give you an idea of where I am on the Dunning-Kruger curve, I'm about there. So I was at Mount Stupid a couple of years ago. What I will do is I'll put up my email address and my Twitter handle at the end of the talk, and if anybody's got any feedback, whether it's good or bad, please do get in touch. Okay, so let's get started. So the first thing I want to show you is this. So this is an example of Li-Fi, of data transmission using light. In this case, the data is music. So this is adapted from a schematic I found on GitHub, and the link will be in the references slides at the end of the talk. And essentially what this is you've got a headphone jack playing in through a phone, playing music, but instead of headphones, the output is to a breadboard of white LEDs, which will modulate according to the data stream, and then the other circuit is a photodiode connected to a speaker. So that was my reaction when that actually worked. And then I did the same thing with infrared LEDs. So exactly the same setup, but using infrared rather than white light. So that kind of concept of visibly transmitting data got me interested in air gaps and jumping air gaps. So I'm going to show you 3 tools I've built in-house at PwC that jump air gaps using light and sound. So some caveats on any research to do with air gaps. The first is that we always assume that the attackers managed to infect at least one host on that air gap network. Secondly, that the attacker has physical or near physical access to that compromised host. And lastly, because when we're talking about exfiltration from air gap systems, we're talking about very primitive outputs. So things like heat, sound, lights, RF emanations, that kind of thing. So it's going to be very slow, and the bits of data we're exfiltrating are going to be very small. So there's been lots of research previously on jumping air gaps. Guys at Ben Gurion University in Israel have done absolutely loads, probably starting with Van Eck freaking in the 70s, which was to do with RF emanations on cathode ray tube monitors. But since then, there's been lots of research. The guys down at the bottom, Hassan and others in 2013, looked at using ambient light sensors on mobile devices to control phones that had been affected with malware. Now, they were only looking at mobile devices, and their kind of attack scenario was an attacker who was able to control overhead lighting in order to influence the values read in by that ambient light sensor. So I applied the same thing to a laptop, to a desktop operating system. Now, ambient light sensors are fairly benign in their purpose. The idea is that they will automatically change the screen brightness depending on the amount of ambient light. And the idea is to kind of reduce eye strain and save battery life, that kind of thing. What an ALS is, it's a hardware component that adjusts its resistance according to the amount of light that hits it. So the same kind of thing you get in night lights. And they can range from very simple to very complex. There is also a Windows API that lets you read programmatically those values that come in from an ALS. So my plan for the first bit, this kind of first bit called the Sensor Darkly, was to create malware that could read in light intensity values from the ALS and then execute different commands according to the sequence of those changes and the intensity of them. A couple of problems with that. First off is I needed to try and make it a covert activity, given we're talking about air gaps. It's not particularly covert to shine a massive torch onto a laptop to execute commands. And the second was, how do I turn that into some kind of exfiltration capability as well? So here's the video of the first problem solved. So this is using a laser from distance mounted on this, this clamp here. And you'll see when I shine the laser at the ambient light sensor, I'm able to pop calc. So that's with a visible laser, but you could potentially do that with an infrared laser as well. In terms of exfiltration, I use this. So this is a light to frequency converter. This is an incredibly sensitive light sensor. They're very cheap, but they're so sensitive that they can measure changes in light through your hand. They can measure changes in the bioluminescence of bacteria, that kind of thing. So I've hooked it up to an Arduino here, just breadboarded it out. And the idea is that the malware, when exfiltrating a file, will use the set device gamma ramp API in Windows. The reason it uses that instead of WMI to change the screen brightness is that WMI requires admin privileges, but set device gamma ramp doesn't. So it actually just changes the gamma level according to whether a bit in a file is a 1 or a 0. In actual fact, what it does is when it starts exfiltrating, it takes a baseline of the current gamma level, and then it makes very small changes in that value depending on whether it's a 1 or a 0. So here's an example of this working. So here's the device. There's a micro SD module as well to save the data. This is the malware running on a victim machine. And it's just going to read in the text file, convert it to ones and zeros. And then it's going to make very, very subtle changes in the gamma value, which you might be able to pick up. So there was one just there. And if you go over to the attacker's machine, this is what's being saved to the micro SD card. You can see we've got like a kind of wave that corresponds to those ones and zeros that the attacker can then take from that micro SD card and demodulate back into the data. So what you end up with is something like this. So the breadboard is not particularly covert either. So I came up with this. So this is the same micro SD module with an Adafruit Flora board connected to the same light to frequency converter with conductive thread. And this is sewn into the back of a tie. It's very light. The tie folds back over it. So you could essentially exfiltrate data just by sitting in front of a laptop as the screen changes. Okay, the next thing was Dreadphone. So Dreadphone is exploring command and control using near ultrasonic sounds. So humans theoretically have a hearing threshold of 20 hertz to 20 kilohertz. In reality, most adults can only hear up to about 15 or 16 kilohertz. So sounds which are between 16 kilohertz to 20 kilohertz we call near ultrasonic. And actually a standard laptop sound card is perfectly capable of transmitting and receiving sounds at those frequencies. So there's been previous research on using near ultrasonic tones for command and control, Tofsted and others in 2010 and Hansbach and Gertz in 2014. Both of those researchers and other researchers who've looked at this previously have experienced a problem when they've tried to do this. So here's an example. So this is a series of near ultrasonic tones. So whilst you can't hear the tones themselves, what you're actually hearing here are the electrical clicks made by a discharge on the sound card, which obviously make it a lot less or a lot more obvious activity. So to get around that, I did this and applied multiple fade-ins and fade-outs to my malware. So Dreadphone uses 16 pre-prepared WAV files that have had this fade-in and fade-out and amplification applied to them. Each tone represents a hex character. And here's an example of this. So you have the victim on the right and the attacker on the left. So they're both monitoring the input from the microphone. Notice my elite GUI skills as well. So what the attacker is going to do is going to send a command to the victim to just pop calc, and that's going to send a particular sequence of those WAV files, which are then going to be picked up by the victim, who's then going to pop calc. And then the next thing I'm going to show is exfiltration. So I have like a text file on the victim's laptop, which just contains a very short string. And then the attacker is going to send a command to the victim to tell them to exfiltrate that data. The attacker is going to then receive it and demodulate it back into the original text. So if I stay with the attacker here, what you'll be able to see is those tones coming back. And then you can retrieve the original text. So there is a case study of this being used in the wild. If you've heard of Bad BIOS, which is malware from a couple of years ago, that actually infected the network of the founder of Pwn2Own. And whilst it did kind of really sophisticated tricks with the BIOS of an infected machine, it also allegedly communicated with other infected hosts in the proximity of it using near ultrasonic tones. So Dreadphone is fine for kind of bits if you want to exfiltrate bits and quite small pieces of data, but what if you want to exfiltrate something larger, like an image? So you could use the same technique, but it would take a long time. So I developed a tool called Spectrogram, which does exfiltration by encoding or embedding an image as sound. And this is a technique that's been used in popular music. So there are two examples here, both from different songs. It's quite kind of a niche thing to do, but some musicians do it. And the idea is you read in an image, you iterate through the pixels, and then you output a WAV file that contains frequencies distributed according to those pixel values. And when you view that audio as a spectrogram, which is a visual representation of the frequencies in a piece of audio with frequencies on the y-axis and time on the x-axis, you can recover the image. So there are open source tools that will do this, Coagula, Spectrology, and things like that. I came up with an example. So you've got an image like this, which is just a screenshot of a password. You would load up Spectrogram, load the image in. You can select a minimum and maximum frequency, so we're sticking with near ultrasonic tones here, and that outputs a WAV file. Now, if you just play that WAV file, you shouldn't be able to hear anything because it's at near ultrasonic tones. But if you use a free tool to view the kind of spectrogram layer of that audio, then you can retrieve that image. So this could also be used for steganography, albeit it's almost better than steganography because you don't need the original file. You just need to record the audio that's coming out. Now, the other thing that you can do with Spectrogram is you can also merge that secret file with a legitimate audio file, which is what I've started to do there. So I have an image file, I have an audio file here, which just plays a piece of music. And what I'm going to do is use that and merge that with my secret WAV file. That's going to write me out another WAV file, which when I play it, will play the legitimate audio. And then when I view that piece of audio as a spectrogram, I can still recover that secret message. So in terms of mitigation for the air gap bypasses that I've showed you here, you'd be looking at things like removing or disabling ambient light sensors if they're not required. Privacy filters for laptop screens do a really good job of muting screen brightness and gamma changes. In terms of sound, you could be looking at white noise generators, ultrasonic tone detectors, or even disabling microphones and speakers if they're not required. Okay, so part two, surveillance and counter surveillance. So the first thing is a laser microphone. I assume lots of people in this room have heard of laser microphones before. For those of you that haven't, they're essentially a long-range audio surveillance device. So the idea behind them, they've been around for a long time. If you're doing surveillance on someone across the street and they're having a meeting behind a window, and they've got the curtains closed so you can't kind of record what's going on, let's assume you don't have any assets in that room, either no bugs or no sources or anything. What you can do is shine a laser at the window. As those people in that room are talking, they're making air molecules vibrate, which makes the glass in the window vibrate. As you shine the laser beam at the window, the reflected laser beam that comes back to you will be moving backwards and forwards. You capture the reflected laser beam with a photodiode, and as that reflected beam travels across the surface of that photodiode, it generates changes in voltage, which you can then convert back to audio. So it's allegedly been used, or was used, to confirm the presence of bin Laden in his compound in Abbottabad, and there's been various other believed instances where it has been used. So I came up with a really cheap version of this. So on the left, what you've got is the listener module. This is adapted from an electronics kit that was meant to do something else. What I've got at the front of it is a photodiode, very cheap. And then the output is a 3.5 millimeter female audio chassis. So you can plug in headphones or speakers. And on the right, I've just got a very cheap, nasty laser module. So I'll show you a demo of this working. So what I've got here is the listener module connected to a speaker and the laser, which is on at the moment. And at the other end of the table, I have a phone that's playing music very quietly. Taped to the back of the speaker on the phone is a bit of reflective material. At the moment, the reflected laser beam is blocked by a bit of plastic. And if I remove that, so obviously that was very cheap. The whole thing together cost about 25 to 30 quid. Now you can get these commercially, albeit they're generally only sold to law enforcement and intelligence agencies. But you're looking at kind of tens of thousands of pounds because of the stability that goes into the laser and the audio processing and stuff like that. But you can see if you can do that with about 25 to 30 quid, if you were to invest a couple of £100 in it, you could actually make quite a viable device. And there's all sorts of things you could do to kind of clean up the audio as well. Okay, so moving on to infrared signals, so sniffing, analyzing, cloning infrared. So it's a very similar principle to RF signals. We're only going to be talking about fixed codes, fixed infrared codes, but essentially the process is the same. You need to find a way to listen to the signal, a way to analyze it, and then a way to replay it. And if you're interested in infrared exploitation, there's a really good talk by Major Malfunction from DEF CON quite a while ago now, in 2005, which was about compromising hotel payment systems via the infrared. So in terms of sniffing the signal, you can actually use an RTL SDR to do it. Because they're based on TV tuners, they do have an infrared receiver. You need the RTL IR library, which you can get from GitHub, and that will return you raw pulse data, undecoded pulse data, if you point a remote at it. You could use a dedicated infrared receiver and an Arduino. And the nice thing about this is if your remote uses one of the popular consumer protocols for infrared, it will automatically decode it for you, which is the case here. So this was from my TV remote, the standby button, and you can see it's decoded it as the NEC protocol, and it's giving me the value. And the other thing you could do is you could use a photodiode. So this is the listener from the laser microphone. So I've got an infrared remote. And the nice thing about that is it lets you inspect the wave visually, so you can actually see what's going on. In terms of replaying infrared signals, if it's a known protocol, something like NEC, as it is here with my TV remote, then you can use something like the iRemote library for Arduino, and you can just play back that value. If it's an unknown signal, then you have to do something similar to what you do with RF, which would be kind of read the edges and the delays into an array and then play that whole array back. So in terms of using this practically, a good example is passive infrared motion detectors. So Porter and Smith in 2013 gave a talk at Black Hat USA on various ways you can do this. I think there was a Mythbusters episode about how to bypass passive infrared motion detectors as well. Things like moving slowly, using reflective surfaces to mask your body heat, and overwhelming the sensor with heat like a flame. So this is an example of a passive infrared motion detector. The grey circle, the grey sphere, is the actual infrared sensor itself, so that's what triggers it. The red window that you can see on the top left, that's a normal infrared receiver for the remote. So the remote itself uses infrared, which is a bit of a weird design choice. The remote can arm and disarm the system. On the right, I've got an Arduino circuit and an infrared LED, which can perform a clone and replay attack for that remote. So I'll just show you an example of that. So I'm going to arm it first and just check it works. So that works fine, and then I'm going to activate the Arduino board, and it's just going to clone the disarm signal. Right, now there's nothing kind of particularly interesting about that. It's just a really simple clone and replay attack, except it uses infrared. And in fact, from an attacker's point of view, there's two problems with this. The first is, given it's infrared and it's short range because it's consumer infrared, how can we learn the disarm signal in the first place? We'd either have to put a device nearby, near the system, or we'd have to try and get hold of a remote when no one else is around and capture the signal. And the second problem is, if you've got a device on Arduino that has got the disarm signal programmed into it, how do you get close enough to actually disarm it and be sure that you're not going to set off the alarm yourself? So in terms of the first problem, how do you learn the disarm signal? I bought 9 of these alarms. So these are all manufactured by the same company, but they're sold under 3 different brand names, one in the UK, one in the US, and one in Australia. And I sniffed the arm and disarm signals from each of those remotes. So each purchase, you get the system and you get a remote. And I think you'll see the problem here. So out of the box, by default, any remote will arm or disarm any system. So all an attacker needs to do is know that you've got one of these, and they can just go and buy one, and then they can then disarm your alarm. And just to prove that's true, if I pick up a remote at random, and then if I pick up another remote, so that's the first problem taken care of. The second problem, I guess, is kind of negated by solving the first problem. But because I had some spare time, I came up with a couple of solutions to get around that as well. So the second problem is, how do you get close enough whilst being sure you're not going to trigger the alarm? So this is the first instance. Drone to clone to pwn. So the reason I've used a drone here, and specifically the Parrot AR drone in this case, this takes about 35 to 45 seconds of being in the air before its lithium battery gets warm enough to set off a passive infrared detector. So what I've done here is I've just mounted that Arduino board on top of the drone, and I've used the Parrot's internal USB port to power it. So I've got the alarm in the foreground here. As you can see, I've dressed up for the video. So you can see if I try and approach it, it detects me, as it should. So I'm going to demonstrate my elite drone flying skills. And I don't know if you heard, but it disarmed it while it was in the doorway. Second solution is this. So this is phone to clone to pwn. So this is using a GSM breakout board for the Arduino. So it has a SIM card in the back of it. It has a phone number. You can text it and call it if you wanted to. And the idea behind this is you would hide this device or pay someone to hide this device near the alarm during the day when it's disarmed. And then all you have to do from anywhere in the world is text a particular string to that number on that SIM card, and it then activates the infrared LED and disarms the alarm. So this is based on Sami Kamkar's digital Ding Dong Ditch, if you've seen that, which did the same kind of thing with a wireless doorbell. Couple of differences is that this doesn't use interrupts to check messages, it just uses a loop. It obviously uses infrared rather than RF, and it also deletes text messages off the SIM card once they've been read. So as usual, what I'll do is I'll arm the alarm first and just test that it works. This is the sketch that's running on the Arduino. So in this case, it's looking for a particular string in a text message, that string being new phone, who dis. And then on the next check, that message will be read, the string will be verified, and it will send the disarm signal. So just to check that, if I have another look at the Arduino sketch, you can see that the message has been opened, it's been read, it's sent the evil signal, it's then deleted it off the SIM card. So you could combine both of those techniques together, and you could phone a drone to clone to pwn, but that would be ridiculous, so I didn't do that. Okay, active infrared motion detector. So this is a slightly different kind of system. You have two parts to this, a transmitter and a receiver. The transmitter is sending a constant pulse of infrared signals to the receiver. And if those pulses are broken, then the alarm sounds. And if you permanently remove the transmitter, then the alarm will continuously sound. So what you can do is create a device which just clones a signal from the transmitter. And that's then kind of accepted as the new transmitter, and you can move freely in that area. So in terms of mitigation for laser microphones and infrared alarms, in terms of laser mics, you could deliberately induce vibrations on window surfaces. You could use things like wire screens and coverings on windows. You could try and detect infrared lasers with unfiltered cameras. Double glazing and curved glass can cause problems with laser microphones as well. And in terms of alarms, ideally you'd want to use physical keypads to disarm, not remotes or anything that can be kind of remotely sniffed. If you are using remotes, you want to go for ones which ideally use RF and encrypted rolling code algorithms, and maybe have anti-jamming as well. Kind of astonishing, I have to say this, but remotes that are paired uniquely to a device is always a good idea. Okay, part three, BANTs. So the first thing I want to show you here is delayed auditory feedback. So this is also known as speech jamming. It's a technique that's been around since the 50s, and it's kind of based in psychology and neurobiology and that kind of thing. It was originally developed as a technique to help people who stutter. The idea is that you introduce a latency between someone speaking and them hearing themselves speak. Now, if you use this on someone who doesn't have a stutter, it induces mental stress, and it basically inhibits their capability to speak properly. So a couple of researchers tried this out in 2012. They built a hardware version. I built a software version called Doublespeak. Now, you might have seen videos of people trying this out as well, and there are kind of free websites that do this as well. In terms of kind of evil applications for an attacker, it's limited, but you could do some stuff with this. So you could, for instance, if you're on a network, sow discord and disruption by using this on a really important conference call or something, because it does really stress people out. And to illustrate that it stresses people out, here are some of my colleagues trying this out. So what these guys are doing is they're reading a paragraph on a website, they're wearing headphones, and my script is running on this laptop. And what it's doing is recording the sound of them speaking, and then it's playing it back into their headphones with a delay of about 200 milliseconds.
consist of extending and so on between speech and auditory perception.
Delayed auditory feedback, also called delayed side tone, is a type of altered auditory feedback, which is extending the time between speech and auditory perception.
Delayed auditory feedback, also called delayed side tone, is a type of altered auditory feedback that consists of extending the time between speech and auditory perception.
Use of voice and headphones and fraction as later. Some DX devices are hardware, DX software is also available. Most delays produce a noticeable effect of between 50 to 200 milliseconds. DAF usage with 175 millisecond delay has been shown to induce mental stress. Surely there's a stress problem.
Okay, so that's speech jamming. The next thing, demotivating malware analysts. So this is inspired by Christopher Domas, who gave a talk on this at RECon a couple of years ago. The talk was called Psychological Warfare in Reverse Engineering. And he created a tool that generates working malware that when viewed as a flow graph in a disassembler, shows an image of the attacker's choosing. So in this case, it's a skull and crossbones, but it could be anything. And this is actually working malware as well. So I wanted to come up with something similar using light and sound. It's not quite as sophisticated as what Chris came up with. But let's say you're a malware analyst and you're analyzing a piece of malware. And when it's run, it makes this sound. So you'd want to know kind of where is that sound coming from? What does it mean? So you disassemble it. In this case, it's just a .NET exe, so very easy to disassemble, and pick out the resource that's causing that sound, which is just a WAV file embedded in the malware. So you can imagine it would be driving an analyst mad trying to work out what this WAV file does, what it means. You know, is it trying to exploit something? Is it encoded? Is it encryption? Is it some kind of communication? And then eventually it occurs to you to look at it as a spectrogram. And you see something like that. Okay, next up. So this is probably the thing I'm proudest of, anything I've ever done, Gilmore Gilmore. So to give you a bit of background on this, my wife is a huge Gilmore Girls fan. She watched it when it first came out. It recently came back on a popular streaming service a couple of years ago. And since then, she's watched season 1 to season 7 about 80 times. And in that time, I've gone from kind of passive indifference to, you know, it's not really for me. I can see why people might like it, to active hatred and loathing. And I hate everything about it. I can't. So if I was in a mature marriage, we'd probably just talk about it. But instead, I came up with this. So Gilmore Gilmore is 2 parts. It's a Python script that uses a brilliant open source music recognition library called Deja Vu. And the other part is an Arduino device. What Deja Vu does is it listens to audio coming in through the microphone, and it compares it to fingerprinted MP3 files in the database. So it's music recognition. So what this Python script does is it uses the Deja Vu library to listen to 10 seconds of audio every 10 seconds, compares it to a song in the database, which is the Gilmore Girls theme tune. And if there's a match, it sends a byte down the serial port to the connected Arduino device, which has an infrared LED, which clones the standby signal for my TV. So this is the kind of upshot of that. I've been advised that there's possible copyright issues with playing the audio. So I've got a video without the audio, and I'll upload the full video to YouTube at some point. Here you go. So this is the kind of pre-credit sequence. Okay, so there's been 10 seconds with no theme tune, so the script assumes all is well. The theme tune kicks in. So you could actually combine that with any theme song or song you wanted. The next step for this is voice recognition. So to turn off the TV anytime a member of the Kardashian family speaks. Okay, and the last thing I wanted to show you is Astro Drone. So Astro Drone is disrupting drones by echolocation jamming, essentially, on their ultrasonic altimeters. So I've used a parrot to demonstrate this because I had a parrot lying around and it's got an ultrasonic altimeter, but it's not specific to parrot. I'm not picking on them specifically. Any drone with an ultrasonic altimeter is likely to be affected by this. So what these do on a drone is they're normally on the base of it, and they're a tool to work out how far away the drone is from the ground. So it's basic echolocation. It sends out an ultrasonic pulse at a particular frequency. That pulse will then hit an obstacle, and the receiving component on the altimeter will receive that bounced ultrasonic pulse back. And then based on the pulse width, the navigation board can infer how far away the drone is from the ground. So what you can do with this is you can perform echolocation jamming. So you essentially emit your own ultrasonic frequencies aimed at the altimeter, and it confuses the drone. 8 times out of 10, it causes it to launch upwards at speed. 2 times out of 10, it causes it to try and go down through the floor because it assumes it's either at maximum or minimum altitude and has to adjust accordingly. So it's very similar to research published last year by Liu and others at DEF CON, which was the similar kind of attack against Tesla S cars. So you can use something as simple as this to do it. This is an animal repellent device that you can buy online. This has got a passive infrared detector. And the idea is if a cat or a dog or something walks past this, then it sends out an ultrasonic pulse at an adjustable frequency, which is meant to scare that animal away. If you use it on a drone, this is the result. So you'll notice that what happened was the drone actually kind of ignored the land command and just kept on trying to go up until eventually it panicked and you end up with a broken drone. So what I wanted to do next was try and see if I could make this a more dramatic effect. So that was kind of fairly powerful, but I wanted to try something else. And I also wanted something where the drone didn't have to fly directly over it, could do it at an angle. So I came up with this. So that's a colander because I ran out of money. And what you've got there are 4 passive infrared sensors. Underneath this colander is an Arduino Uno, 2 Arduino Unos actually. And then you've got 18 ultrasonic transducers that are all configured to send pulses at the same frequency as the drone's altimeter. Now, interestingly with this, I've used infrared here to detect a drone. You could also use that Deja Vu library from GitHub to perform acoustic recognition on a drone. So if you record the sound of a drone flying in a particular environment, a particular model of drone, and save that as an MP3, you can then compare incoming sound into a microphone to that database, and it will pick up the sound of the drone. So you could also use acoustic detection for this as well. So in terms of real-world applications for that, you could use that essentially as a kind of drone repellent to keep drones away from particular buildings or events and stuff. At PwC, we're doing more research on this, so we're testing this out with different kinds of drones and different kinds of devices to emit ultrasonic pulses. The other interesting use case is you could use this as personal drone protection, like this. Okay. So to sum up then, this is an overview of the research I've done on light and sound, and you can see there's quite a lot of links between the different techniques and topics. And you can interpret this one of two ways, either that I was following a really careful and comprehensive and structured plan, or that I've just cobbled this together to give the illusion of structure once everything's done, to try and get more research funding. So in terms of pros and cons for an attacker using light and sound, it's great for things like physical engagement. So if you're doing secure environments that use air gaps, it's very difficult to detect and defend against from a defender's point of view. There's very little trace left of activity once an attack has taken place. And as you could probably infer from this talk, it's very cheap to test this stuff out. You can kind of tinker with stuff and try stuff out very cheaply. On the downside of it, you do need to be close to targeted systems in most cases, subject to interference like environmental interference. So for instance, laser microphones are affected by things like rain and snow and kind of traffic noise, that kind of thing. And the range and power you generate very much depend on the resources that are available to you. In terms of mitigation, first step's knowing that this stuff exists and that it's possible. And I guess that inputs and outputs can be manipulated pretty easily. So ideally, you would either block those inputs and outputs completely, or you'd ensure that there's like a reliable failover. So the drone, for instance, rather than just relying on an ultrasonic altimeter, would also use some other kind of means to detect where it is. Clone and replay attacks very much still possible. And there are limitations with a lot of security products. So motion detectors, for instance, it's not enough just to say we have a motion detector. Often they're susceptible to various kinds of attacks. Future research, I will look at exfiltration via infrared, acoustic keylogging, some kind of automated solution for that, some more work on Li-Fi, and then some more work on drone repellents, as I mentioned. So hopefully, in terms of how you feel about this presentation, you're on the left rather than the right. All the music that was used in this talk was royalty-free and acceptable for commercial use. There are references slides here. So this PDF I can make available online. It's also available on the DEF CON media server as well, if you want that. Or just get in touch and I can happily supply you with these details as well. So as promised, there's my email address and my Twitter handle. Thank you very much. It's been an absolute pleasure. Yeah, thank you.